Hey everyone, welcome back to Professor Stephen Williams. He is continuing with chapter 5, going over motor installations.
Okay guys, this is basically a review for a quiz we're having tonight, and since I've already done some videos associated with the first 4 parts of chapter 5, I'm not going to repeat them. But I did do some dubbing on part 7 and 8 on the PowerPoints, and from what I can see, they didn't turn out so well. It looks like you can't click on them, either that or maybe it's just my computer at work, I don't know. But either way, I'm going to go over these and kind of repeat some of the stuff that I put in there. Again, for all of this, I want you to keep an eye on the big picture, not the infinite details that are there. All right, so now we're looking at motor installation. And when we get into it, you know, a foundation's pretty important if you have the option of what you're going to do to it. Obviously, if you've got a motor that's already mounted in a piece of equipment, you're kind of stuck with what you got. However, if you're going out and actually installing a motor, typically you're going to want a very firm, strong base, okay? Concrete, steel. A lot of times what they'll do is they'll put embedments in concrete to give you a good firm foundation to mount the motor to. Okay, so with that in mind, that's an important thing, and a lot of times there's nothing you can do about it because you're stuck with what you got. Okay, when you mount it, basically, unless otherwise, basically keep the motor tightly mounted, okay? Not to the point of breaking bolts, but keep it to the point where it's not going to start moving, loosening up, mounting bolts and stuff like that. When you get into like belt-driven and gear-driven, you end up creating some transverse forces. For example, things at 90-degree angles to the actual shaft of the motor versus an axial load, which is typically what's happening when you're going in line with your load. So belts, again, where you have something like that, having some flexibility in being able to move the mount so that you can tension or detension the belts is a very, very good thing to have. All right, rigid base, 9 times out of 10 that's your preferred thing. Sometimes you're going to find motors that a resilient base is something that's somewhat flexible. It's got some flexibility built into the mount. The purpose of it is to isolate vibrations from the motor, passing it on to the equipment itself. And along that line, there are applications, but most of the time you don't want to use something like that again when you've got a transverse load on there. Inline, yeah, could work a little bit, especially if you've got a flexible coupling, which is not unusual when you've got an inline load. So you've got a motor inline with a pump, for example, or a fan. All right, the Nemesis face mount, that's something where you're mounting it directly to the equipment. Sometimes you've got a pump where the motor mounts directly to the pump, so it bolts right up to it. All right, and you've still got the shaft, of course, being fed through. But there's other times, like for example, we use them quite frequently on motor-operated valves. There you've got an actuator that's attached to the yoke of the valve, and the valve is driven up and down. Okay, the shaft of the valve is driven up and down by a motor that's got a gear on it, and the gear interfaces with a shaft that's a threaded shaft. It's like a, I wouldn't call it a rack and pinion, but it's a worm gear typically. All right, and that again would bolt directly in. Typically what you've got is a motor where the holes in the motor are threaded and you're bolting through from the structure that you're mounting to. But again, those are pretty much the only three options you're going to have there. We'll find out later on that motors, for the most part, don't care which direction you mount them. The only problem is that you usually don't want to have them facing up or facing down unless that's the way they were designed. Because if they're facing up, facing down, you end up putting stress along the direction of the rotor, and most of the bearings are not designed to handle that stress. So unless you have a thrust bearing in there, like with a vertical motor, the motors are actually designed to be able to handle a vertical. The bearings in there are thrust bearings, and quite frankly, I've seen some huge ones, and oftentimes they're in an oil bath. Okay, when you're getting involved with pulleys and gear drives, again, alignment is the utmost importance. Any deviation on alignment is going to be transmitted between the motor and the driven load, and it's probably going to end up messing up both the motor and the driven load. So be that a fan, whatever. So keeping it aligned properly is extremely important, and the time you take doing that is well worth it. Believe me, these things are not cheap, and if you have to go out and replace sheaves, replace gears, replace drives, it can get pretty expensive. So a lot of times the electricians that I work with at FPL, the only thing they get involved with is when we've got a belt-driven load. However, when you're outside in a contractor, you're basically doing whatever you're given to do. And again, I've seen them take days getting the alignment down properly. Usually the test of the alignment, when you're all said and done, even though you think it's perfect, the test of the alignment is a vibration test after you're all done. And if you've got low enough vibration, your alignment's good enough. If it's too high, time to get rid of it. Redo it and replace it. Okay, so they make tools, lasers that aid in the alignments. But again, you've got all kinds of different problems you could have. I'm looking for, oh, I guess it's not here. Yeah, that's what I was looking at right there. Okay, so there's all kinds of different alignment problems you could have where the load and the drive are not perfectly parallel with one another, where one's in head of or in back of the other. Okay, again, you're going to go through a belt very quickly there. You're going to tear out bearings. Okay, so they're made for a very specific type of load, and they can't handle much in the way of misalignment. So I can't overemphasize that. Okay, going back a little bit, direct drive motors, as the name applies, supplies torque to the speed, to a load directly. Motor coupling, okay. Typically the direct coupling, 1-to-1 ratio. In other words, you're not doing anything to change the speed. Flexible coupling permits the motor to operate the driven load while allowing for slight misalignment. In other words, they make flexible couplings that allow when it says slight, it's real slight, okay? So a lot of times they're plastic and they're able to move independent of one another as they're spinning. In other words, what I'm talking about here is one where you've got a shaft in line with a shaft. Okay, so a driver in line with the driven. And you have bolted shafts where they bolt up together with flanges, all types of different arrangements. So flexible couplings do exist, but again, they're not going to allow for much misalignment. If you find yourself doing it, get some flexible couplings if you can. However, if you've got severe misalignment, they will wear out in no time. Okay, variable diameters. Okay, well, if you're dealing with pulleys and gears, for example, you basically, and the book goes into it, I'm not going to try to repeat it here, but they give you basically some information, and these are posted in the
Canvas.
the actual PowerPoints are posted online, so you can go in and look at them in our assignments, previous assignments. Okay, where you've got variable diameters, okay, basically when you're looking at, okay, the circumference is proportional to the diameter, okay? So if you've got for example, a 6-inch diameter, a 12-inch diameter, okay, they're actually going to have a 2-to-1 speed ratio, all right, because what you're looking at is the belt is riding on the circumference, and the circumference of the circle is pi times d, okay, so the speed, therefore, of which they're covering the belt is covering the diameters would be proportional to those diameters, okay? So if I've got a motor speed, for example, with a 12-inch pulley on it, let's say, I'm just talking off the top, 1800 RPM, okay, and it's got a 12-inch pulley and a shaft for a fan, for example, that would have a 6-inch pulley. The speed would be, again, proportional diameter, so the fan speed would be 3,600 RPM. Or you can change them around the other way and decrease the speed of the driven. Okay, so that's the way you do it. Gears are the same, only the difference there is you're looking at where the teeth actually hit each other rather than the inner circumference. So it's a little bit different, and you have to get that information basically from the gear manufacturer as to what the effective diameter of the gear is. So they have gearboxes that they use for speed reductions and speed increases, so those things are kind of built into the design of them. Moving along, again, variable speeds are possible by making available different gear ratios and pulleys with variable diameters. And looking at this, obviously, motor RPM, motor pulley diameter, equipment RPM, it tells you that they're inversely proportional to one another. Sorry. Okay, there's a little problem there. You've got it in your book. You can look at it, go through it. All right, now, I failed to look at what type of tension you put on the belt when, I'm sorry, this is looking at the tension on the belt, but it's looking at a deflection. But the deflection is based on a certain amount of force that you're putting down on there, and I failed to look that force up, but we can, and you can get that online. But essentially what they look at is, if you look at the span, which is center line to center line of pulleys, and it's going to be 1/16 of an inch per inch of span. So if I have 10 inches between the two pulleys, you'd have 10/16 or 5/8 of an inch of deflection from top to top as you push down on it gently. And again, usually they use a push-pull gauge to figure out the tension that they put on there. And I just can't remember what that tension is, what the push-down force is. Okay, misalignment, we talked about that. Motor bearings. All right, motor bearings, again, usually they're not really listed on the motor nameplate. If they are, that's very fortunate because I seldom see them listed on there. But it makes it a whole lot easier to try to find out what replacement you want to use. However, they're made fairly standard now, so you can use different manufacturers for bearings as replacement. Essentially, you've got several different varieties. They're always lubricated. Typically, small ones are lubricated with grease. As you get to the larger size ones, and again, it depends upon the type of bearing you've got. For example, usually a split sleeve bearing, or a what do you call it? The I'll get to it in a minute. The different kinds of bearings, we'll get to them in a second. But anyhow, oil is usually used on the split sheave. If you've got the roller bearings and ball bearings, typically you're going to have grease in there. Sometimes they're expected to be maintained periodically. Other times they have sealed bearings that are not expected to be re-greased. So it behooves you to find out what type you've got. Obviously, typically if you buy a motor and there's no provisions for adding grease, you've probably got permanently sealed bearings. All right, if there are provisions, if there's Zerk fittings, for example, to put in grease, chances are you need to be doing that periodically. All right, that's the sleeve bearing. Typically, you're riding on a shaft, the sleeve bearing goes around it between the case, and you've got a layer of oil. The system is set up basically to keep a layer of oil circulating through that bearing at all times. Goes down through a filtration system and back up again. And sometimes they even have oil coolers depending upon the size of the bearings. They might have water going through an oil cooler to keep it cool. Otherwise it could heat up as you go along. Ball bearings, very typical when you've got inline to inline, where you've got a driver in line with the driven, quite frequent with pumps that way, because then you're not trying to transmit any transverse loading on it. It's all axial loading and basically torsional loading. All right, and they're ideal for that. All right, both not lubricating and over lubricating bearings can damage them. Okay, the key, if you've got a bearing that you grease, typically there'll be two paths. There'll be a pass in, and there'll be a path in and a path out. You don't want to have that path out go into the motor. So look to see, a lot of times you'll have a discharge where the grease will come out of the bearing through a hole, and then you pump until you see the new grease coming out again. That's not an unusual way of doing it. Other times they recommend so many cubic inches of grease, and you take a little cubic inch type thing and count how many pumps it takes to fill up a cubic inch, and you put that many pumps in it. That's, believe it or not, that's how they do it. Okay, but again, you pack it full of grease. Now you start creating more pressure, okay, and again, that's going to wear out things too. Our roller bearing, now you're getting into something where you're looking at the possibility of transverse loading, because again, rather than a ball, okay, has basically at any one point a single point of bearing, okay, where a roller has a linear line of bearing. So theoretically infinitely more surface area. However, it is, you can't might, take it into the atomic level. So this gives you a chance to give it more bearing surface in the transfer direction. If you've got a motor that's driving a gear drive or a fan with pulleys, for example, you're going to have transfer loading, and that should be the kind of bearing you've got in there. Okay, so again, depends how you're going out to buy your things. If you have to replace a motor, look at it. If it's got fans on it, if it's got sheaves on it or gears on it, chances are you're going to need some roller bearings. This is what I was trying to think of before. I'm sorry, the thrust bearing. Typically the thrust bearings are lubricated in an oil bath. Quite frequently on the very large motors, they have very large thrust bearings. I've seen some that have been literally several feet in diameter. Okay, and along that line is, some of those are 4,000, 5,000 horsepower motors. So when you get that kind of load on there, these are designed for the maximum amount of surface in both directions, both in up and down thrust, so axial loading, all right? Because when you're spinning a vertical motor and a pump, a lot of times the pump, while it's spinning, will create forces in the up and down directions as it's spinning. So you have to have a bearing that's capable of handling that load. All right, electrical connections. Again, I'll let you flip through there. They're pretty standard in there. Okay, grounding. We've talked about it more than once, so I'm not going to go into it here. But you've got the equipment grounding conductor, all right, and the ground fault return path. Typically, ground fault return path is internal to the conduits. The system grounding is oftentimes external to the conduits. You might take it to the first ground grid connection that you've got, for example, where you definitely want to create a path for your ground fault return as short as possible between the point that you're grounding, which would be a source of fault current, to the source of that current. And in doing that, you want to use conductors that are sized big enough to keep that load and time down to a minimum. Grounding electromotor also helps to reduce unwanted noise. Yeah. All right, typically in industry, your ground conductor is, the equipment ground conductor is typically uninsulated, although there's no reason why it can't be insulated. Typically they prefer to have it uninsulated so that, number one, it's grounding everything that it passes past, and that's a good thing. So in other words, you'll run an uninsulated conductor parallel to cable trays and oftentimes parallel to conduits, again, to give it as low a resistance and therefore as quick of a job of tripping the source of the current, the breaker, the fuse, whatever. Okay, flexibility, they talked about it there. Oftentimes when you're coming from, for example, the last conduit before you go into a motor, you don't want to transfer that vibration that may be in that motor to the conduit system. So we'll typically use a flexible conduit. Oftentimes in industrial, commercial settings, they'll use what they call basically it's got an insulation jacket on the outside of it, and then it's got the spiral type of flexible conduit internal to it, liquid tight. That's the word I was searching for. Liquid tight, flexible metal conduit. They use special fittings. They're very good. They keep water out. They keep problems out of it, and they even have ground conductors, for example, that travel through the conduit up to say 1.5 inches and 1.25 inches in diameter. I believe above that size, they want you to jumper across the flex conduit to keep a continuity of that equipment ground. All right, grounding the motor shaft. That's something that's, you run into it sometimes if you get into drives, like variable frequency drives. But generally speaking, I haven't run into it in the past. And it's a tricky thing because they're not really set up to try to insulate the shaft. All right. Conductor sizes. All right. This is duplicated in there. Now, if you go to the posted one I have, I believe for Monday, Tuesday this week, you'll find this same thing in there, but I added some additional slides in there. So please go to that because I tried to go over that. I gave you some tables showing you resistances, for example, of different size conductors and how it's easy to get a lot of voltage drop between your source and your load. And again, all of that's based on using the full load current. And usually you use from the NEC table the 430, 250 if you happen to be a three-phase motor. And that current is basically looking at the horsepower size based upon somewhat a worst case scenario of what you're going to find in the industry. All right, there's some problems here, how to look at voltage drops and stuff like that, figuring out what ampacity you need to size your cable for. Go through them, they're important. I don't get into a lot of that in your exams. Okay, for these motors, for example, what I'm looking for, and I think that's where I'm going to leave it at this point because here's what I'm really looking for. Have a general knowledge of motors, okay? What are the two categories? You've got AC, you've got DC. You know, when you get into DC, I'm looking for you to know the 3 different major types, okay? Yeah, there's a lot of subtypes, but I don't care about them. All right, know that you've got a DC motor that's got a series winding. Okay, series with what? Series with the armature. The armature is the rotor, right? So it's going round and round. And what about a series that I expect you to know? I expect you to know basically, big picture, that a series motor has very high starting torque, and it can spin up very quickly. You don't want to start it without a load attached to it. Okay, so think of a series wound as a large conductor, low resistance type winding that's going to put a lot of current through, give you a lot of torque, and if you don't have load to resist that torque, it's going to spin up to the point that you can basically break the motor. All right. The other type of motor I want you to is the shunt wound. Okay, think of a shunt wound as a parallel winding. Parallel to what? To the armature. Okay. And that is a basically nearly constant speed. It's fairly high speed, constant speed, so it doesn't, but it also has fairly low torque in the beginning. But as it's building up its torque, the speed declines slightly, but not much. All right, those are the two things. And again, that winding is a very small wire, very high resistance type winding. Okay, where there might be, in the series, there might only be 1 or 2 loops in that winding. There'd be perhaps hundreds of loops because it is a very small wiring to keep the resistance as high as possible. Again, to give you voltage drop versus not giving you voltage drop. All right, the difference between is the compound motor, which has both series and shunt windings. So both a series and parallel winding, and it has characteristics that are about halfway between the two. Okay, when I'm looking at a single phase AC motor, all right, there's 2 basic types. One is a split phase motor, where you've got a winding parallel to the winding, to the stator winding, and it's off about 90 degrees from the stator winding. And what that does is to get you a difference in rotational action. It gives you the rotational action because now you have 2 different types of power in there. One's attracting, one's pushing away, and you get the ability for the motor to self-start. In a DC, it's typically self-starting, okay, and you generally don't have to provide any extra incentive for it to start. In a 3-phase motor, it's definitely self-starting. Because it has a rotating, by definition, it has a rotating field in the stator and in